Hello students, good morning. We were discussing with the chapter Mechanics of Fluids, and today we will move to one of the property of fluids, that is viscosity. Okay, so our topic is viscosity. Now here I am considering a liquid moving very slowly and steadily over a fixed horizontal surface. Okay, so this is my surface. This is the fixed surface. Now liquid is moving slowly and steadily over this fixed surface. So it will be moving like layers. Okay. So there are various layers flowing steadily and slowly over a fixed surface. Now each layer, you can see in the figure, each layer is moving parallel to one another. Okay, this layer is parallel to this layer. Again this one parallel to this one. So in such a way the liquid is moving. Let us consider like that. Now here you can see this is a fixed surface. So the layer which is in contact with the fixed surface will be at rest. Understand? Now as we go up, what will happen? As we go up, the velocity of each layer increases uniformly. Understand? That means here suppose it has a velocity like this. Now here it is moving faster. Here again moving faster. Here again moving faster, like that. Each layer has a velocity in the increasing direction. Okay. So the layer in contact with the fixed surface is at rest. So at this point, if I am considering here, the velocity is equal to 0. And as we go up, the velocity increases uniformly. Clear? Now here I am considering two layers. Suppose these are the two layers. This one is layer A and this is layer B. You are considering two layers here, and the upper fast moving layer A always tends to accelerate the lower slow moving layer B, while the slow moving layer B always tends to retard the layer A. Understood? That means here these two layers are having different velocities, right? So this layer always has a tendency to move with a faster velocity than this layer. So what will this layer do? It always has a tendency to accelerate, and it will make this layer B also to accelerate with it. Okay, but at the same time, what will this B do? B has a velocity lower than A. So B will tend to retard the motion. Retard means what? Slow down. Slow down the motion of A. Understand? So there is always a force acting here. There is always a backward dragging force acting here, which tends to destroy the relative motion. Okay. To maintain the motion, an external force has to be applied to overcome the backward viscous force. Clear? Here we are considering a fixed surface. Then liquid is flowing here slowly and steadily. Liquid is flowing over the fixed surface. And at this point, near to the fixed surface, it has zero velocity. But as we go up, the velocity increases. Now here you are considering two layers A and B. Now what? This B has a velocity lower than A, isn't it? Now always A will tend to move this B with its velocity. Make the layer B to move with its velocity. Aയുടെ velocity Bയേക്കാൾ കൂടുതലാണ് അല്ലേ? അപ്പോൾ A എന്ത് ചെയ്യും? എപ്പോഴും Bയും Aയോടൊപ്പം വരാനായിട്ട് ശ്രമിക്കും. But at the same time, Bയുടെ velocity കുറവായത് കാരണം B എന്ത് ചെയ്യും? Aയുടെ സ്പീഡ് കുറയ്ക്കാനായിട്ട് ശ്രമിക്കും. So there is always a backward dragging force acting here. Understand? And this backward force is known as viscous drag. What is that? Viscous drag. That is the backward dragging tangential force. Understand? Backward dragging tangential force. You can call it as F. It is known as viscous drag. And what will this viscous drag do? Is it will always tend to destroy the relative motion. Understand? Relative motion means only we can express relative motion with respect to two layers. രണ്ട് ലെയേഴ്സുമായിട്ട് കമ്പയർ ചെയ്യുമ്പോൾ ഇതിൻ്റെ മോഷൻ കുറയ്ക്കാനാണ് ശ്രമിക്കുന്നത് അല്ലേ. എ മൂവ് ചെയ്യുന്ന ഒരു വെലോസിറ്റിയിൽ പക്ഷെ ബിയുടെ വെലോസിറ്റി ഇതിനേക്കാൾ കുറവായത് കാരണം ബി എപ്പോഴും ബാക്കിലേക്ക് വലിക്കും അല്ലേ. ആ ലെയറിനെ ബാക്കിലേക്ക് വലിക്കാനൊരു ടെൻഡൻസി കാണിക്കും. അപ്പോൾ ദർ ഇസ് എ ചേഞ്ച് ഇൻ വെലോസിറ്റി. Isn't it? ആ ഒരു ബാക്ക്വേർഡ് ഡ്രാഗിങ് ഫോഴ്സിനെയാണ് എന്ത് വിളിക്കുക? വിസ്കസ് ഡ്രാഗ് എന്ന് വിളിക്കുക. ക്ലിയർ? എക്സാമ്പിൾസ്, സപ്പോസ് ഇഫ് യു ആർ സ്റ്റിയറിംഗ് എ ലിക്വിഡ് contained in a beaker with a glass rod. Understand? Suppose you are considering a beaker like this. Okay. Now beaker consists of water. You are stirring it with a glass rod or a spoon or something like that. So what will happen? It starts rotating like cylindrical layers. Like this it will rotate. Isn't it? Okay. In this way the water will rotate. But after some time when we stop stirring, what will happen? The speed of the different layers gradually decreases and finally the water comes to rest. What does it show? As it shows that an internal friction comes into play which destroys relative motion between different layers. നമ്മൾ നോർമലി ഇപ്പോൾ രണ്ട് സർഫസിൻ്റെ കേസ് പറയുമ്പോൾ നമ്മൾ ഫ്രിക്ഷൻ പറയാറുണ്ട്. സോളിഡ് ഫ്രിക്ഷൻ എന്ന് പറയും അല്ലെ. കുഞ്ഞു ക്ലാസ്സിലെ പഠിക്കുന്നതാണ് ഫ്രിക്ഷൻ. സെയിം തിങ് ഫ്ലൂയിഡിൻ്റെ കേസിൽ വരുമ്പോൾ നമ്മൾ അതിനെ എന്ത് വിളിക്കും? വിസ്കസ് ഫോഴ്സ് എന്ന് വിളിക്കും, അല്ലെങ്കിൽ വിസ്കസ് ഡ്രാഗ് എന്ന് വിളിക്കും. അണ്ടർസ്റ്റാൻഡ്? സോ ഓൺലി ബിക്കോസ് ഓഫ് ഫ്രിക്ഷൻ ഈ ലെയേഴ്സ് എന്ത് ചെയ്യുന്നു? യെസ്, ഇറ്റ് ഈസ് കമ്മിങ് ടു ഇറ്റ്സ് റെസ്റ്റ് പൊസിഷൻ. ഓക്കെ. ഈ നമ്മൾ സ്റ്റിർ ചെയ്യുമ്പോൾ അത് നല്ല സ്പീഡിൽ കറങ്ങുന്നു, പക്ഷെ കുറച്ച് സമയം കഴിയുമ്പോൾ ദ ലെയേഴ്സ് വിൽ സ്റ്റോപ്പ് ഇറ്റ്സ് മോഷൻ. Isn't it? The speed will decrease and finally it will come to rest. That means that there is some internal frictional force acting inside the fluid which destroys the motion between different layers. Understand? So that's an example for viscosity. Okay. So how can you define this viscous drag? It is the backward dragging tangential force which tends to destroy the relative motion. Okay. Suppose if you want to maintain the motion, what will you do? Yes, you have to apply an external force. You have to apply an external force which can overcome the backward viscous force. Understand? So this is one of the example that we can use in the case of viscosity. Now the second example, if you are taking two liquids such as water and honey in separate funnels. Okay. You can see that the water comes out readily from the hole in the funnel, while honey trickles down drop by drop very slowly. Isn't it? Why? Because honey is more viscous than water. Honey has more viscous force. That is why there is a backward drag. Backward dragging force is more than water. Every fluid has a viscosity, but some fluids are more viscous. Okay, honey, then glycerin, like that. They are having viscosity higher than water. So their motion will be slow when compared to that of water. Understand? That is also one of the examples. Then another example you can say, you can walk fast in air but not in water, because as the viscosity of air is much smaller than that of water. Inside water there is a viscous drag which is very high when compared to the viscosity of air. Okay. So the viscosity of air is very small when compared to viscosity of water. That is why you can walk fast in air but not in water. Understand? So these are all some basic applications of viscosity. Clear? So how can you define viscosity? It is the property of fluid by virtue of which an internal force of friction comes into play when a fluid is in motion and which opposes the relative motion between its different layers. Okay. So when the fluid is in motion, there is always an internal force of friction which comes into play. But it depends, it varies depending on different liquids. Understand? For water there is a viscous force, but for honey there may be, the viscous force may be more. Like that, for different liquids this viscosity or the viscous force will be different. Understand? And this motion, this force opposes the relative motion between its different layers. Understood? Now we are moving to the next term, which is again important one, that is coefficient of viscosity. So for studying this coefficient of viscosity in detail, again I am considering a fixed surface here. Okay, a fixed surface is considered. This is the fixed surface. Okay, now here again the liquid is flowing in layers like that we have discussed in the previous case, and two layers I am considering here. First one like this, now second one like this, because the two layers are parallel to each other, that is why you can draw like this. So these are the two layers, and let the layers be P and Q. Okay, this is P and this is Q. These are the two layers parallel to each other. Understood? Now these two layers are at a particular distance from the fixed surface, right? Suppose this is at a distance of x from the fixed surface. Then this is at a distance of x plus dx. There is a small difference, right? That can be taken as dx. So x plus dx is the distance from this solid surface. Also, you know, as we are moving up from the fixed surface to different layers, the velocity increases. So if this layer has a velocity of v, this layer should have a velocity of v plus dv, isn't it? Anyway, this will be more than this v. So I took it as v plus dv. Okay. So from the fixed surface, the distance of p is x and distance of q is x plus dx. Clear? Also the velocity, as it goes up, the layers has a higher velocity. So it is v, then this is v plus d. Understand? Now, if you if you take the change in velocity, what is the change in velocity? Yes, it is v plus dv minus v, which is dv. Clear? What is the change in distance? X plus dx minus x, which is dx. Okay, so you got the change in velocity as well as change in distance. Okay, so the rate of change of velocity with distance is known as velocity gradient. The rate of change of velocity with distance is known as what? Velocity gradient. That is dv by dx is known as velocity gradient. Okay, velocity gradient. And this velocity gradient is in the direction of increasing distance. Is in the direction of increasing distance. Okay. Now, I just told this because we are going to study in detail about coefficient of viscosity. While discussing coefficient of viscosity, we need this term velocity gradient. That's why I told this velocity gradient. How will you define velocity gradient? Yes, it is the rate of change of velocity with distance. Okay, in the direction of increasing distance. Clear for you? Okay. Now, according to Newton, a force of viscosity F is acting tangentially between the two layers, isn't it? Suppose if it is flowing like this, in this direction if it is flowing with the velocity of v plus dv, and this is flowing with the velocity of v. I told that in between these two layers there is a viscous drag which tends to move in the backward direction, isn't it? So there is a force here which will act like this, and this force is called the viscous force. So always this viscous force is in the opposite direction to the direction of movement or direction of motion. Understand? So viscous force is acting like this. Now, according to Newton, this viscous force depends upon certain factors. First one is viscous force, or F, is proportional to area of the layers in contact. Understand? Viscous force F is proportional to the area A of the layer in contact. That is the first point. Now, second one is, again, this viscous force is proportional to the velocity gradient. Viscous force is proportional to the velocity gradient. Clear? So these are the two factors on which viscous force depends. So combining these two equations, you will get F proportional to A dV by dx. F proportional to A dV by dx, isn't it? So this constant of proportionality can be changed so that this will become F is equal to minus eta, okay, minus eta A dV by dx. Understood? F proportional to A dV by dx. By combining these two equations, then this sign can be changed by multiplying it with a constant which is minus eta. So F is equal to minus eta A dV by dx. Then what is this eta? This eta is called the coefficient of viscosity. So what is this eta? Yes, it is the coefficient of viscosity that we are discussing. Okay, coefficient of viscosity. Now you can see a negative sign there. What does it mean? This negative sign shows that the viscous force acts in a direction opposite to the direction of motion of the liquid. You know, as liquids, the layer of liquid is moving in this direction, but the viscous force acting is in the opposite direction. So this direction can be shown with the help of a negative sign, so that F is equal to minus eta A dV by dx. Understood? Now, how can you define this coefficient of viscosity? This coefficient of viscosity can be defined as the tangential viscous force. Okay, that means when you are taking this area as well as dV by dx as unity. Normally we define the constants like that, isn't it? The terms that are along with the constant, you make it as unity, or you will put the value 1 for each physical quantity, and then you can define the constant. So if you are putting A and dV by dx as 1, you can write the equation as F is equal to minus eta. What is the condition? Is when A equals 1 and dV by dx is equal to 1. Okay. Now how can you define this coefficient of viscosity? As it is defined as the tangential viscous force required to maintain a unit velocity gradient and unit area, or you can say unit velocity gradient between two parallel layers each of unit area. Clear? Once again, when you are putting the value A equal to 1 and dV by dx equal to 1 in this equation, you will get F equals minus eta. So now you can define this minus eta or eta. How can you define? Omitting the negative sign, you can define it as it is equal to F. F is our viscous force. So it is the tangential viscous force required to maintain a unit velocity gradient between its two parallel layers, each of unit area. Clear? So that's how you can define coefficient of viscosity. You can note down the definition. Okay, the coefficient of viscosity can be defined as the tangential viscous force required to maintain a unit velocity gradient between its two parallel layers, each of unit area. Okay, now about the dimensions of coefficient of viscosity. Dimensions of eta. Okay. So first of all, write the expression eta is equal to, you know, F is equal to what? Eta A dV by dx. Clear? So what is eta? Eta equal to F by A into dx by dV. Right? F by A into dx by dV. So write the equation here. Negative sign I am not taking. F by A into dx by dV. Okay, now what is the dimension of force? You all know, that is ml t raised to minus 2. Dx is distance, so I can write it as L, divided by area is L squared, and dV is lt raised to minus 1. Okay, now you can clear it. So here one L square is there, L square get cancelled. Remaining L is there, it will go there. So first m, then L raised to minus 1. Okay, then t raised to minus 2 and t raised to minus 1 in the denominator. This will go up, it will become plus 1. So minus 2 and plus 1 will give you minus 1. That is t raised to minus 1. So m, L raised to minus 1, t raised to minus 1 is a dimension of coefficient of viscosity. Understand? Now about the units, first of all the SI unit is Poiseuille. Okay, Poiseuille, Poiseuille, the SI unit of eta. Okay, now the second CGS unit is poise. CGS unit is poise. Clear? So there is a connection between this poise and Poiseuille, that you can write it as 1 Poiseuille is equal to 10 poise. 1 Poiseuille is equal to 10 poise. Clear? So that's all about coefficient of viscosity. So next our topic is Stokes' law. Okay, this is very important. Here actually the viscous drag on a body falling through a liquid is explained. Viscous drag on a body falling through a liquid. Clear? So suppose there is a fluid here. Let us assume like that. Now in this fluid, this is a, suppose you consider this as a viscous fluid, then I am putting a body into this fluid. Okay, so the layer of the fluid in contact with the body moves with its velocity. Okay, when a body falls through a viscous fluid, the layer of the fluid in contact with the body moves with its velocity. The fluid at large distance from it remains at rest, isn't it? So when it falls, the layer which come in contact with that body will move with its velocity, but the layers which are at a larger distance from this particular body will remain at rest. So there is a relative motion, isn't it, between different layers of the fluid. As it is having different velocities, there is a relative motion. As a result, if there is a relative motion, it experiences a viscous drag that we have explained before. and this drag or this retarding force increases with increase in velocity of the body. This retarding force increases because it is proportional. Okay, when the velocity increases, retarding force also should increase. Understood? That is, when a body falls through a viscous fluid, the layer of the fluid in contact with the body moves with its velocity. Okay. However, the fluid which is at large distance from it remains at rest. So this produces a relative motion between different layers of the fluid. As a result, the body experiences a viscous force which tends to retard its motion. This retarding force increases with the increase in velocity of the body. So according to this law, according to Stokes' law, you can state the law as the backward viscous force acting on a small spherical body of radius r moving with uniform velocity v through fluid of viscosity eta is given by, there is a relation, that is F is equal to 6 pi eta RV. Okay, so when I am putting a small spherical body into a viscous fluid, it experiences a viscous force, and that viscous force can be written like this. That is, 6 pi is a constant, eta is the constant coefficient of viscosity, r is the radius of that spherical body, and v is the velocity of that body. Understand? So it is directly proportional to the radius as well as it is proportional to velocity. So with whatever velocity, if the velocity is increasing, if the velocity of the body is increasing, the retarding force that it experiences also increases. If the radius is large, yes, it has a huge or high retarding force or viscous force. Understand? So that is what Stokes' law is giving, and you can prove this Stokes' law with the help of dimensional analysis. Okay, so let us look how to derive this Stokes' law. First of all, you have studied how to derive an equation with the help of the given data, with the help of dimensional analysis. That is, here the viscous force F acting on sphere moving through a fluid depends on, the factors are the coefficient of viscosity, this is given, okay, coefficient of viscosity eta, then the second one is radius of the spherical body r, then the third one is velocity of the body, velocity v of the body. Okay, so the viscous force F acting on a sphere moving through a fluid depends upon the coefficient of viscosity eta, radius r of the spherical body, and velocity of the body. So with this given data, you can frame an equation. How will you write the equation? As F is equal to K into, I don't know the power or the order of each physical quantity, so I just write eta raised to A, okay, then r raised to B and v raised to C, where eta is the coefficient of viscosity, r is the radius of the spherical body, v is the velocity of the body. Okay, K is a dimensionless constant. Now here you know the dimensions of each physical quantity. For F you can write it as m L t raised to minus 2 is equal to K into, the dimension of coefficient of viscosity is ml raised to minus 1 t raised to minus 1 raised to A, r you know it is L raised to B, and velocity you know that is LT raised to minus 1 the whole raised to C. Clear? So in such a way you can equate, that is the powers on left and right can be equated. How? Is equating the powers of m, l and t on both sides. You will get for m, here you can see it is 1. Okay, this is 1. And here also it is 1 raised to a, which we can write it as a is equal to 1. Equating the power of m, we will get a is equal to 1. Now for L, check here, left side it is 1. L have the power 1. And here you can see L raised to minus 1 whole raised to a, that is minus a. Okay, then L raised to b, that is plus b, then L raised to c. So minus a plus b plus c is equal to what? 1. Clear? And the third one is for t, here it is minus 2. Here it is t raised to minus 1 the whole raised to a, that is minus a, and here it is minus c. So minus a minus c is equal to minus 2. Now you can solve, that is you have the value for a, put this in equation 3, that is minus 1 minus c is equal to minus 2. Minus c is equal to minus 2 plus 1, which is minus 1, or c is equal to 1. So you got the value for a, then you got the value for c. Now you can put the value in this equation, second equation, so that you will get the value for b, that is minus a is 1, minus 1 plus b, then c is also 1 is equal to 1. Okay, that is b is equal to 1. Here 1 and minus 1 will become 0, 0 plus b, which is 1. So a equal to b equal to c is equal to 1. You got like this. Clear? Now you can put the value in the above equation. In which equation? As here in this equation for a, b and c you can put the value. So this equation will turn to f is equal to k eta r v. Eta raised to 1, r raised to 1, v raised to 1. Understand? Now for a small sphere, this k is found to be equal to 6 pi. So f is equal to 6 pi eta rv. F is equal to 6 pi eta rv. Clear? So this proves Stokes' law. Understand? So the Stokes' law, actually it is giving the viscous drag on a body falling through a fluid, and it is said that the backward viscous force acting on the small spherical body of radius r moving with uniform velocity through fluid of viscosity is given by the expression f is equal to 6 pi eta rv, which means that as the radius and velocity increases, the viscous force also increases, and you can prove this relation with the help of dimensional analysis. So you will get the expression as f is equal to 6 pi eta rv, where 6 pi is a dimensionless constant. Okay, then we can use this equation for numerical section also. Okay, so that's all about Stokes' law. So today we have discussed viscosity, regarding viscosity, then second one is coefficient of viscosity, then third is Stokes' law. Okay, so you can write the notes while I teach. You can prepare it and keep it with you, and stay safe. Have a nice day and thank you.